咁我就將以下嘅時間咧就交俾Arab 嘅講者阿 Alexis 同大家講解一下，多謝晒。
OK， 各位好，我係 Alexis。先喺呢度多謝歡迎各位同業嚟參加今日2019風荷載規範嘅簡介啦。咁頭先阿 Fion 都頭先阿 Fion 都介紹咗啦，今日主要嚟講咧係分咗3個大部分啦。第一個部分就係關於2019規範同2004版入邊嘅更改啦，而第二部分咧就會係關於一啲案例，由我同事阿立川一陣間會再用案例去 demonstrate 究竟個規範會點樣使用，然後最後一個 section 咧就係關於 Q&A 嘅。咁根據呢個規範嘅使用，第一件事需要大家可能要知道嘅就係根據2004版一樣，就係喺使用之前，大家係需要做一個好簡單嘅測試，就係話你嘅樓宇係咪適合用到呢個規範咧？咁喺2004版入邊其實已經提出咗，如果你個 building 係有非常之 unusual shape 啦，或者有一個好 complicated 嘅 topographic surrounding 咧，你已經需要去做 internal test 㗎啦。咁喺2019版入邊咧，係增加咗一條款，就係如果你嘅 building 嘅高度咧係超過200米嘅話，你亦都係需要進行 internal test 嘅。如果你嘅 building 符合晒所有呢啲嘅應該話 exempt from 呢啲原則嘅時候咧，你就可以利用2019年去按照規範嘅內容嚟驗算你嘅荷載。咁荷載規範入邊嘅荷載可能要分2大部分啦。第一部分就係關於樓宇結構方面嘅荷載啦，另一部分咧就係立面方面嘅 cladding 嘅承載嘅 pressure 或者佢嘅結算佢嘅承載力。咁簡單啲咁講啦，喺building 方面，第一個就係可以利用規範去計算出風力嘅荷載作為承載力同埋呢個stability 兩方面嘅考慮啦。然後喺新嘅規範入邊亦都多咗一項，就係呢個舒適度嘅考慮。咁一陣間我哋會詳細逐步咁去解釋嘅。而佢整個程序點樣去運用個規範咧，就喺規範入邊本身就有一個flow chart， 我哋可以按部一步咁走，就可以計算出你需要嘅荷載㗎啦。咁而喺立面方面咧，亦都同樣係俾你可以計算到風力嘅壓力啦。然後利用個壓力都可以計算出你構件上邊嘅承載力。咁呢個程序上亦都係有一個 flow chart 喺入邊，喺 Figure 2.2入邊咧，你只需要按部就班一路按住程序走咧，你就可以計算到出嚟嘅。咁或者我哋再深入一啲講一講關於結構荷載方面嘅折算嘅方法同埋佢嘅分別喺2019同2004版。咁如果你睇到圖嘅左手邊就係一個簡化版嘅2004嘅流程。點樣去折算你嘅風力荷載、結構嘅荷載？而喺右手邊咧就係2019年版。咁喺兩本規範入邊咧都有第一樣嘢需要計算嘅就係一個順向風向嘅風力計算啦。咁你睇到兩個粉紅色框住嘅位置就係佢兩個折算嘅方法啦。咁然後跟住喺2004版本身嚟講咧，其實都有需要去計算嘅所謂嘅橫向風同埋扭力嘅折算嘅，但係當日嘅規範咧就冇好詳細咁列出計算嘅方法，係需要你去參考一啲其他嘅相關嘅文獻。咁但係喺新版入邊咧，我哋就直接有一啲equations 啦，係可以直接計算出咗所謂嘅橫向風同埋扭力嘅承載力嘅。然後跟住喺舊規範入邊咧。你係需要計算所謂嘅diagonal wind 同埋本身 XY wind 嘅。咁喺新規範入邊咧就簡化咗，其實而某程度上，我哋只需要計咗 XY wind 之後，利用 XY wind 利用呢個 load combination 咧去 combine 兩個 XY wind 咧就可以達到以前計呢個diagonal wind 或者係 along wind 嗰個XY wind 嗰個折算方法㗎啦。咁如果再睇落去。關於2004版以前計算呢個結構順風向嗰個折算嘅時候咧，以前係有2個方法去做嘅，一個咧就叫 static approach， 另一個就 dynamic approach。咁依家2019年版咧，其實就簡化咗嘅，我哋只有一個 approach， 一個叫 unified approach。咁就算係 static 或者 dynamic 咧，都可以用呢個 equation 去計算嘅。 咁如果你睇到呢個表啦，呢個表入邊好反映咗幾樣嘢。第一就係以前2004版喺圖嘅左手邊就係佢以前你點樣去計算 long win low 嗰個數值啦。而喺2019版入邊嚟講咧，其實計算嗰個程序同2004版基本上係相類似嘅。而新增咗嘅部分咧，就係依家喺綠色個框綠色嘅部分咧，就係喺2019年版入邊新增加嘅部分嚟嘅。而同時間咧，喺計算design win reference pressure 啦、force coefficient 啦同埋 size dynamic factor 呢方面咧，係有一個升版喺入邊。咁一陣間喺後邊幾張 slide 入邊咧，我哋會逐一咁介紹嘅。咁係啦，咁我哋先講就係 directionality 啦。directionality 嚟講咧，如果同業有經常接觸到關於例如用風洞試驗去設計嘅時候，都會發現到其實喺香港喺唔同嘅風向吹嘅時候咧，係有一啲相應嘅節減嘅。咁喺規範入邊，我哋將佢規範化咗，咁變咗咧，如果你一 building 喺唔同個 orientation 唔同嘅時候，可以根據佢嘅坐向嚟 apply 呢一個 coefficient 嘅。咁相對嚟講喺西北方向嚟咧，個風向係可以節減得最多嘅，就喺呢個西北方向啦。而最大風向嘅地方咧，就喺呢個東北同埋北邊方向嚟，就係東南方向嚟咧，係比較上咧係會係大嘅。咁但係呢個都好容易就可以 apply 得到噶啦。而同時間，如果你個標坐向唔係完全正北啊、正南咁咧，你可以用 interpolation 嘅方法咧去計算相關嗰個數值嘅。咁咧，跟住呢張 slide 咧，我哋就可以睇到關於呢個 sheltering 嘅 effects， 呢個亦都係一個新嘅 feature 嚟嘅。咁喺圖嘅右手邊嘅一個wind reference pressure 咧，其實同2004版相對嚟講係冇改變嘅，係絕對 exactly 一樣嘅。咁喺以前2004版入邊咧，就等於 case one 啦，因為以前冇 sheltering 個考慮嘅。咁例如一個 building 係200米嘅，我哋想知道佢150米嘅時候嗰個 reference pressure 咧，咁你直接喺個表度就可以度到出嚟㗎啦。咁但係如果我哋 apply 咗sheltering 嘅時候，我哋係可以計算一個節減嘅高度節減嘅係數。當你計算咗個高度節減係數之後咧，相對嚟講，你個風壓嚟講咧係可以相應咁減低嘅。所以但係實際嘅程序咧，我喺下一步喺我同事咧會喺 part 2入邊咧會詳細咁再解釋俾你點樣操作。咁另一個 update 啦，頭先講啦，就係關於呢個關於其中裏邊每一個以前嘅 design win pressure 啦、force coefficient 啦同埋 size dynamic factor 本身入邊嘅修改。但係 for design win reference pressure 頭先都講咗，其實本身個 pressure 本身咧係冇修改嘅，只不過因為加多咗 directionality 啊、sheltering 喺入邊咧，所以佢相應嚟講都係有咗一個升版嘅。咁喺依家見到嗰張 slide 入邊咧，大家見到就係以前2004版，大家點樣去計算個 force coefficient 啦，係 based on table D1 同埋 D2 啦。咁新嘅咧2019版咧，我哋就用咗一個 graphical 嘅代表，咁只需要你計算咗個 B over D ratio 啦，或者同時計埋個 HE over D 呢個 ratio 嘅時候，你就可以直接喺個表度揾到你相對需要嗰個數值啦。但係同時間，因為方便大家嘅計算啦，呢一嘅年代大家都用電腦去做嘅時候，所以我直接就將一條 equation 係放咗喺個規範入邊，只需要你按照呢條 equation 計算嘅話，你都可以得到相同嘅答案嘅。咁另外一樣嘢有個 feature 喺入邊係舊規範嚟講咧，呢一個 feature 咧，其實就需要你哋去按照一啲literature 啊 special literature 去揾嘅。咁但係我哋依家相對嚟講就將呢啲 feature 咧都放埋落去個規範入邊啦。比如上一個 building 喺佢哋嘅corner 上面，佢有 round corner 啦，或者有個 cut corner 咁咧，其實呢個 effect 咧對風嚟講係有一定嘅節減，所以我哋將呢個節減係數亦都放咗落去規範入邊。而以前喺舊嘅規範入邊都有另一個問題出現，就係有啲 building 係相對係 regular 嘅 irregular shape， 咁大家對於 determine 佢個 B 同 D 呢兩個 ratio 嘅時候咧，都會有一啲不同嘅考慮，亦都有不同嘅意見。咁所以咧，我哋喺呢方面咧，就直接將一啲比較上我哋叫做規矩啲嘅 irregular shape 咧，都放埋喺規範入邊，可以俾大家有個參考，就知道點樣去計算個 BD 呢個 ratio。咁用呢個 ratio 嘅話，你就可以用翻前邊嗰條 equation 咧，直接就計算出嗰個factor 出嚟啦。咁喺舊規範同新規範咧，都有呢個 dynamic factor for a long win 嘅。咁你都睇到啦，喺圖嘅左手邊就係以前舊嘅 equation 啦。咁大約有8條左右咧，1、2、3、4、5、6、7條。咁喺新嘅規範嚟講，我哋就將佢簡化咗少少，就變咗3條 equation。咁亦都係話可以直接就可以利用呢個 special 啦，就可以計算得到呢個 dynamic factor。好啦，咁之前都講咗啦，其中有一個喺舊規範入邊冇好明確嘅equation 或者係一個程序去做嘅，就係一個 coarse grain 嘅 assessment。當一個 building subject to 一個 significant 嘅 dynamic response 嘅時候咧，你係需要去揾一啲相關嘅 special literature 去做一個 reference， 或者要去做 internal test。咁依家喺新嘅規範入邊咧，就有個比較簡單嘅程序，尤其是喺 torsional win 啦、torsional low 啦，你只需要按照 cross 2.2.2啦嘅 equation 咧，你就可以計算得到出嚟㗎啦。而喺 along win 方面咧，就有 equation 2-2。咁喺下一張 slide 度面，我哋可以見到嗰條 equation 係點樣嘅。咁呢條就係equation 2-2，就係用嚟計算個 cross win 㗎啦。而同時間咧，喺 cross 2.2.2咧，亦都有一個簡單嘅方法去計算一個 torsional moment， 只需要按照 eccentricity 同埋一個順向風或者橫向風嘅 loading， 咁只計算咗個 envelope case 出嚟，攞取大嗰個 value 嚟用就得㗎啦。好啦，關於 low combination 啦，喺 low combination 方面咧，咁之前舊規範就好簡單啦，都係話你要計4項等於 x、y 跟住 u、v，which is diagonal v。咁但係喺新嘅規範嚟講咧，反而應該係最簡單咗，因為當你計咗所謂嘅 x、y win 嘅時候，你只需要用個 low combination 嚟做咧，你就可以將佢加上嚟，就係1加 0.0。1加 0.5， 然後再加 torsion factor 0.5 torsion， 咁如此類推咧，有三個 low combination 嚟要考慮啦。OK， 之前都講咗啦，喺呢個舊規範同新規範都好啦，都有一個 requirement， 就係究竟個規範本身適唔適合你個 building， 需唔需要考慮一特別嘅情況啦。如果你超出咗規範嘅用途嘅時候，你就會需要走去做 internal test 啦。但係喺呢個新規範入邊咧，如果你個 building 嘅 cross wind effect 係 significant 嘅話咧，當個 cross wind係大過個 along wind by 1.5 倍嘅時候，呢個亦都係需要進行呢個 internal test 嘅驗算嚟再證明，因為個規範本身係有一啲嘅 limitation 入邊嘅 equation 咧，喺一啲超高層上面或者一個超 slender 嘅 building 上面咧，係唔係太合適嘅。咁第一個頭先我哋之前嘅啲 slide 都已經 show 咗啦，就係點樣去計算個 long win 啦，同埋利用 equation 2-2就可以計算 from 一個 cross win 嘅 moment 出嚟。當你將兩個 equation 兩個 value 相比嘅時候，如果係大於 1.5 嘅話，就需要去做 wind tunnel 啦。頭先再 repeat 咗頭先講過嘢啦。咁其實呢一個某程度上係一個相應翻喺2004版入邊7.6個 clause 一樣啦，就係當你個 cross wind 係 significant 嘅時候，當超出咗規範能夠容許嘅程度下，你就可能就需要去做用 internal test 去 verify 翻你個 wind load。咁另外頭先講咗亦都有個新嘅 feature， 就係關於舒適度啦。喺以前嚟講，做舒適度嘅 assessment 咧，就需要你係做 internal test， 然後先至可以 assess 得到嘅。咁但係依家有咗呢條新嘅 equation 喺入邊咧，你哋就可以直接可以計算到出嚟。但係同樣有個 limitation， 就係頭先我講，如果你個 cross wind effect 太大嘅話，呢個 equation 都可能唔適用嘅。咁同時間咧，喺比起舊嘅規範嘅做法咧，依家有一個新嘅 acceptable criteria。呢個 acceptable criteria 咧，相對嚟講係一個 frequency dependent 嘅，即係話你個 building 係一個唔同嘅 frequency 下邊咧，你個 acceptable criteria 係會 varies 嘅。 咁係即係一個更加精準嘅方法去折算你個舒適度同埋一個 compression 嘅。咁喺規範入邊咧，你以下嗰幾張 slide 咧就有一啲比較上係side tracks 比較上 minor 啲嘅 features 喺入邊 ，which 我哋都放埋去規範入邊嘅，比如 template structure 啦。template structure 嘅 window 大家都知道，喺舊嘅 pinnap 啊入邊都係用緊，可以話用top 7成嘅。咁例如計算呢個 hoarding 啊，一啲 non-residential 嘅 template structure，例如 bamboo shed 啊，咁咧就可以用到37% of 嗰個 wind pressure。咁呢件事以前咧喺 pinnap 入邊嘅，咁我哋亦都將佢規範化咗，將佢放埋落去個規範入邊，咁就變咗大家可以唔需要再去抄 pinnap 啦，直接就喺規範入邊可以引用到呢啲嘅 benefit 啦。咁另外一樣 feature 係喺個規範入邊反映嘅，亦都增加咗喺入邊嘅，就係喺舊嘅2004版入邊咧，就話steel structure 同埋 concrete structure 咧，只係俾咗一個數值 for 呢個 damping 嘅。咁但係佢有條尾喺度嘅，有少少就係話，如果你個 building 咧係好 slender 嘅時候，或者係個 stocky 嘅 building 嘅時候咧，其實呢個 value 咧，你係需要再 assess 嘅。咁亦都係需要你哋揾一啲 special 嘅 literature 特別嘅相關嘅文獻嚟參考嘅。咁但係亦都因為咁咧，所以我哋就直接俾咗一個 reference，就係將比較 stocky 嘅 building 咧，例如細個細嘅，咁佢嘅damping ratio 係一個咩 range 咧？咁我哋都喺今次喺個新規範入邊就升咗版，將呢個數字都放咗落去啦。咁同時間亦都將計算 structural loading 同埋計算舒適度兩方面喺最新嘅 research 入邊反映到佢哋嘅分別咧，亦都喺呢個新嘅規範入邊咧，其實係反映咗噶啦。咁另外喺呢一張 slide 入邊見到啦，就係喺香港亦都有好多情況出現，就係一啲叫做我哋叫做大底盤多塔樓嘅情況，而喺舊嘅規範嚟講咧，大部分只係apply for 一個 single tower 啦。咁我哋依家喺新嘅規範入邊咧，我哋就嘗試去俾一啲 guideline 出嚟，去點樣操作，能夠將呢啲咁嘅情況咧，都可以係折算得到嘅。咁但係因為呢個暫時都係喺一個 research 嘅階段啦，我哋揾到嘅文獻唔係好多，所以將呢個 guideline 咧就放咗喺呢個 expenditure note 入邊作為一個參考嘅。咁大家就可以利用呢個參考，可以睇下點樣去運用啦。咁佢呢個張 slide 就 show 到個 allowing 嘅 case 啦，就係sorry 唔係 allowing 係 translation 嘅 window case 啦，而後邊呢一張咧就係一個 assessment for 個 torsional case 嘅。咁喺個 EN 入邊有個比較詳細嘅解釋嘅，咁大家可以 refer 到嗰度去參考一下。咁第二部分喺第一 part 嘅第二部分咧，就係關於立面所謂 cladding 嘅何在。喺新版入邊，其中一個最大嘅升版嘅 reference 咧，就係以前舊版2004入邊計算個風壓嘅時候咧，係根據佢嘅 reference height 嚟計算嘅。咁但係喺依家新版入邊咧，嗰個 pressure 個 reference 咧就只係剔咗。應該話相應嚟講就係剔咗喺個 reference height 上邊。呢個咧其實咧就係喺咁多年大家好有機會參與到 wind tunnel test 嘅人咧，發現到呢個係一個常態嚟嘅，亦都係一個比較合理嘅 latest research。所以我哋就將佢常規化放翻落去規範入邊。而呢個 adopted approach 咧，其實咧喺世界上面好多規範啊，例如 ASCE 啊、BSCN 啊，都係用同一個 reference 嘅其實。咁喺規範入面亦都cladding 呢部分咧，亦新增咗一個叫做 size factor，就係話如果你個 panel 嘅大小咧係會影響到你承受個風壓嘅 probability 嘅，而亦就可以利用呢個表咧，相應翻你哋你哋嗰個 building 個 panel size 咧，就可以 work out 一個可能係一個 reduction， 亦都可能係一個好等於好似 H factor 一樣咧，係會增加嘅 factor 嚟嘅，係相應翻咁多年嘅喺 wind tunnel 入邊嘅 research 反映翻出嚟嘅情況嚟嘅。其實咁佢就分咗3類嘅，一個就 corner zone 啦，一個就 edge zone 啦，然後剩翻嚟嘅地方就叫做 others。咁其實大家都知道啦，通常喺個 edge 同埋一個 corner 嘅地方咧，個 wind pressure 都會大啲嘅。咁呢個其實已經反映咗出喺嗰條 curve 上邊㗎啦。 咁同時間喺 cladding 呢一個部分咧，我哋就增加咗一啲比較細節上嘅嘢，就係例如一啲細嘅 architectural feature 啊，咁我哋都有一啲相應嘅 force coefficient 擺咗落去，咁係增加咗，就變咗可以希望同業方面就簡化大家同業去揾一啲相關嘅literature去計算嘅。同時間例如一啲 freestanding wall 啊，好似 hoarding 啊方面，我哋都補充咗一啲 coefficient 喺入邊嘅。有一啲喺同業方面即係我哋喺咁多年操作上面咧，都發現到有個問題，就係有時好難去 define 啊，就 edge zone，因為喺圖表上好難，通常只係解釋一個 edge zone 喺個 wording 上面，就冇一個好仔細嘅或者係相對個exactly 嘅 location 或者個 definition， 所以今次我哋喺新嘅區份入邊，同埋喺 EN 個 explanatory note 入邊咧，我哋就增加咗個 section 落去解釋，你 apply 個 edge zone 係嗰度有幾喺一邊個範圍入邊咧，我哋叫 edge zone 咧，由邊個風向嚟嘅時候，邊一個 direction 先至係 edge zone 咧，咁我哋係增加咗呢個篇幅喺入邊嘅。好啦，咁另外第三部分啦，就關於 wind tunnel test 啦。喺舊嘅區份入邊咧係冇提到呢一個部分嘅，咁喺呢個新區份咧，我哋就增加咗一個 section 喺裏邊，就將做 wind tunnel test 所需要嘅quantitative guidance 啦，係例如 topographic 嘅大小啦，個 model 嘅大小啦 ，proximity model 嘅大小啦，同埋一啲關於做 testing 嘅時候所需要個 sheltering obstruction 嘅 removal。個做法啦，都喺新嘅規範入邊咧，都增加咗呢個篇幅，等大家有一個 guideline 可以去 follow。而同時間有一個有啲關於我當然做完 wind tunnel test 之後，究竟我哋要取個 value 個 lower bound 係幾多咧？咁亦都喺呢個區範入邊咧，我都有再增加咗個篇幅嚟解釋嘅。咁簡單啲咁講啦，喺舊規範嚟講，2004版，當你係好 unusual 嘅 shape，有 special 嘅 topographic surrounding 嘅時候咧 ，oops 得咗，係 sorry 啊，你跳咗出嚟嘅，唔好意思啊，啱唔啱啊？有啲嘢跳咗啊，唔好意思啊，跳咗出嚟喎。係咪再 share 過？呢個得唔得？得唔得？我 share 咗咯，唔係，冇錯，唔見咗個乜嘢 team，縮咗一個先，呢個再嚟個得唔得？呢個係得唔得？唔好意思，有少少技術上嘅問題。頭先講到啦，喺2004版入邊咧，如果你嘅 building 或者你嘅 surrounding topographic 係比較上 unusual 或者 complicated 嘅時候咧，你哋就會進行一個 wind tunnel test。而喺 wind tunnel test 入邊咧，出嚟嘅 result 有3個 configuration 啦。第一個就係 existing condition 嘅 wind tunnel 個 building 同埋個 surrounding 係 existing 嘅 condition 啦，或者有一個就係 removal condition， 就係將周邊嘅 building 逐一咁 remove 咗佢，然後考慮佢對佢嘅影響啦，同埋就係一個 envelope case of 唔可以少於0.7 of 個曲嘅 along wind， 咁呢個就係舊規範入邊嘅要求，或者係舊規範喺2004版入邊個 practice 嚟嘅。咁喺2019年版入邊咧，如果第一你係超出咗，好似頭先講啦，你大概200米，或者又係同樣有頭先嗰兩個 condition 咧，係一個比較上 unusual 嘅 shape， 或者有 complicated 嘅 topographic 嘅情況下，咁你去進行呢個 wind tunnel， 或者係頭先話喺規範入邊你計完之後個 cross wind effect 比起嗰個 along wind 嘅 effect 大於1.5倍嘅時候，你都會進行一個 wind tunnel test。但喺 wind tunnel test 上邊咧，就有一個情況就可以可以有兩個情況啦。就係頭先翻轉頭去第一個情況就係話，已經一開始你就已經係超過咗200米啦，同埋有嗰啲 unusual 嘅情況啦。咁你做 testing 嘅時候咧，個 maximum value of 你個 wind tunnel result 咧，你係可以係一個 envelope case of 個 existing 嘅 configuration。然後咧喺 removal case 嘅時候咧，你係可以打個8折，或者係7折 of 一個曲嘅 along wind 嘅 envelope case。所以比起以前舊版嚟講咧，204版嚟咧，其實咧做完 wind tunnel test 之後嘅 result 咧係相對咧係優化咗嘅可以。但係如果你唔做嗰個 removal case 嘅時候咧，淨係有 wind existing 嘅 condition 嘅 case 同埋個 compare 個曲嘅時候咧，你要取個 value 個 envelope 咧就要需要打個8折啦，就唔可以好似前面嗰個 case 係做個7折嘅 case 啦。咁但係相對嚟講，你係做少一個 configuration 咯。仲有一個比較重要嘅 point 要咩嘅就係，如果你 follow 2019年版嘅程序去做呢個 wind tunnel 嘅話咧，咁你按照咗個 procedure 去做嘅時候，咁就變咗唔需要好似以前咁係需要去經過 test set，唔需要再 require 個 SEC meeting， 直接就係可以係擺落去個 submission 入邊用。好，立川交俾你啦。我同事立川會往下解釋關於呢個利用呢個 work example 嚟解釋一下點樣操作呢個新嘅風嘅規範。
好，thank you, Alexis. This is Neptune. So following what is described by Alexis, I'm going to show some working examples to introduce the detailed calculation procedure. Within this part, there will be 3 contents. The first one is a general briefing about the sheltering effect calculation. And the second one is an actual working example. This working example is 90 meters tall L-shaped building. And the second work case will be a taller building, so that is about 190. And it's a rectangular shape, also with some corner modification. So we go through the 3 contents one by one. The first one is a general rule on sheltering effect calculation. Alexis has introduced, so it's a new feature in the 2019 code. Within that, if we consider the sheltering effect, we can get some benefit. So we want to touch into more details because this is quite new. It hasn't appeared in the previous code. So the sheltering effect is something, for example, as explained in the first part, if the elevation is 150 meters, so we assess the wind pressure. That is for example, in the 2004 wind code. But now, if due to the sheltering effect, physically it's something like the wind profile is lifted upward. So for example, if we say the displacement height is 50 meters, so then previously we assessed the wind pressure at 150. Now, still for the 150 meters tall, we only need to calculate the wind pressure at 100 meters. So that's the real benefit due to sheltering. So by adopting the sheltering effect, our wind pressure will be reduced from originally 3.05 kilopascal at 150 now to 2.686 at 100. So this is how the sheltering effect will help us. So the key point is how we can calculate the displacement height. The calculation of the displacement height is given in the Appendix A2 in the Code of Practice. So actually, it is controlled by 3 parameters. So here we can see within the formula, we can see the HI. HI is a particular objecting building height. So those are objecting buildings. So HI represents their building height. So you can see the displacement height will be bigger if the objecting building are taller. So the second one is related to the distance from the obstructing building to the target building. So that is xi. So you can see the further a building is located to the target building, the smaller the sheltering effect. So it all makes sense. And the third one is a lower cutoff limit. So this is to make sure that we don't have excessive benefit from the sheltering effect. So next are some general rules. So the rule number one is that if we have only one obstructing building, we shouldn't take the benefit from the sheltering effect. The reason is the sheltering effect is something that we rely on other buildings to provide sheltering to reduce the wind pressure. So we need to avoid the condition that in a certain period within the design life of our target building, then this building may be removed. So that's why if we have only one obstructing building, we shouldn't take any benefit. And the rule number two is if we have more than one obstructing building, so what we need to do is we need to evaluate the exact sheltering benefit from each individual building. So how to do the evaluation? We need to follow the three formulas. But to make the code more user-friendly, we also provide a corner plot. This is in A2.3 in the appendix A2. So this is exactly the same as the three formulas. So then based on this, we can identify the actual sheltering effect for each individual building. For example, the taller one, if we assume it provides the bigger sheltering, so we shouldn't take that into account. We ignore that. And then we keep searching for the second most benefit. So that will be this slightly shorter building, but closer to the site. And then we can take this into account. So the reason why we can take this into account is, so for two individual developments, so the chance of simultaneous redevelopment and the simultaneous removal of two buildings together, the probability is much smaller. So that's why it is allowed to take the benefit of the second. However, there's also a further rule supplemented in the explanatory note. It says, if the two buildings, they belong into the same building lot, so they should be treated as a whole. So that means the two buildings, if they belong to the same building lot, so as highlighted in the black dash box, so they should be removed together. So the reason is within the same building lot, so the chance they are redeveloped simultaneously is much bigger. So that's why we have such a rule. So another case is, so we talk about the condition in the flight ground or flight terrain. But in Hong Kong, actually, we have many locations, it's in a slope terrain. So how we should treat it. So first of all, we should keep a clear idea is the topographic calculation and the topographic effect and the sheltering effect, they should be calculated separately. So then the topographic effect will be can be calculated independently. After that, so for the sheltering effect, we can see if wind blow from left-hand side, for example, that is from the bottom to the top. So it can be an attached flow, so through the slope of the mountain, but it can be also something like a direct purely horizontally. If it blows purely horizontally, we can see the actual sheltering from each individual building. So their effective sheltering height, so that can be highlighted in blue, are smaller than their actual building height. So that means if we take the actual building height as HI, the red one, that will be on the unconservative side. So what we should do is the code say, in this case, we need to calculate the new objecting height starting from the base of the target building. So that's the blue height. So that is on the slightly conservative side. And in the opposite position, if the building is located at the bottom of the hill, and then the wind blow from the top to the bottom. In this case, also two scenarios. So attached flow, it will be the same as the original building height. But if it's purely blow horizontally from the top to the bottom, so the actual sheltering effect will be bigger than the actual objecting building height. So for this, because the codified approach is very difficult to accurately distinguish when will be attached flow, when will be purely blow horizontally. So we take it as a slightly conservative perspective. So we treat this case, we use the actual building height as the objecting building. Okay, so that's the slope terrain condition. And all the previous discussion we consider is a one-dimensional problem. But in the actual condition in a site, it's a two-dimensional, it's a plane. So then the code says for the sheltering effect, we need to evaluate for 4 orthogonal directions. So the 4 orthogonal direction, each direction covers about plus and minus 45 degrees. So that is a 90-degree sector. And if the building height varies across this 90-degree sector, so we should calculate the sheltering effect for each individual building and then do a weighted average. And according to our experience, in the code, it also says it allows the user to do an equal division. For example, within the 90-degree, we can equally divide the sector into smaller subdivisions, but the total number of subdivisions shouldn't be fewer than 4 divisions. And according to our experience, normally if we divide this into more divisions, it will lead a relatively easier calculation. The reason is you can see from the map, if we divide into small divisions, it's more easily for a building to occupy the whole sector. So that will that will simplify the calculation because we don't need to do the weighted average. So that's a brief introduction about the sheltering calculation principle. So now we go to the actual working example. The first working example is an L-shaped building. So this is the map where it is located. It is located in a relatively very dense urban center. And it's not very tall. The total building height is 90 meters. On plan, it is L-shaped building. The breadth is about 40 meters, and the depth on the two sides is about 15 and 25. And because the building is shorter than 90 meters, shorter than 100 meters, so the natural frequency we can use 46/h. So that is allowed by the code. So what we want to demonstrate through this working example is, so first of all, we want to demonstrate what the general workflow to conduct a codified calculation. So the general workflow will be at the very beginning, as Alexis introduced. So we make an initial assessment whether the standard approach applies or not. If it applies, so we move forward to do the along wind calculation. In the along wind calculation, we need, so the first of all is the ref design wind pressure that related to the directionality, sheltering effect, and the topographic factor. Then force coefficient, size, and dynamic factor. Then we can calculate the along wind force. Based on the along wind force and the geometry, so the B/D ratio, we can calculate the torsional load. Then we also need to check whether the building is a crosswind significant. So then we need to see if not significant, what we should do, and if it is significant, what we should do. And finally, it's the load combination. And some bright points or key feature with this particular working example is, so first of all, the crosswind is not significant. So then later we will show another example that the crosswind is actually significant. Another one is we want to use this working example to show the procedure how to calculate the effective height and using a simplified approach. So then we go to the details to the step-by-step calculation procedure. At the very beginning, we need to have an initial judgment within this diamond box. So within this, we need to see whether the building is shorter than 200, yes. And it is Euro shape. And then it is not located in a complicated surrounding or very complex topography. So pass all the through checking criteria. So then we don't need to go to the wind tunnel test. A standard approach applies. The next step, we calculate the design wind pressure. For the design wind pressure, the first step is a directionality. So we need to align our building. So this red box is our building alignment. Then we identify the 4 orthogonal directions. So that's the 4 orthogonal directions. Then starting from the 4 orthogonal directions, so we have starting from the 4 corners, we can identify the 4 different sectors, each cover 90 degrees. So here we want to show that although we start from the 4 corners, but actually we start the 4 corners, then draw a radar plot for the directionality starting from here will be the same as we draw the 4 directions from the center, then draw a radar plot here. So this will make it more convenient. So we start from the center of the building and then draw the radar plot. So the table A 1.1 will give the directionality for all the 8 key directions. So then anything in between, we do interpolation. So that will be the radar plot. Then we use one sector, one of the 4 orthogonal directions as an example. If wind blows from the right to the left direction, so that will be Wx1 minus. So you can see it covers the northeast, that will be 0.84. The east will be 0.85, and the southeast, that will be 0.85. So we pick up the maximum among the 3, the directionality factor will be 0.85. So that's the directionality factor for Wx1 minus. So then we do the sheltering effect assessment. So we use a simplified approach because the building is located according to the EN, as say in Appendix A 1.2. There's a detailed discussion to say if the building is located in a very dense urban center, the surrounded buildings are of similar height of our target building. We can use a simplified approach to assess the effective height of sheltering effect. That will significantly reduce the complexity of the calculation procedure. So here are some general steps what we should do. First of all, we consider a range. The range is normally recommended as the smaller one between 500 meters and 6 times of the building height, the target building height. So the 500 meters is not a hard number. So if you want to go to 600, that's also fine. If you go to 300, it's also fine. It's not a hard number. But the general principle is the bigger the circle you draw, possibly the bigger the sheltering benefit you can take. However, if the distance is taller than 6 times of our target building, there'll be no benefit at all. So the recommendation is never to go beyond 6 times of the height of our target building. So that's the first step. The second step is based on the building alignment. So we need to identify the 4 key orthogonal directions. So each cover 90 degrees. Then a further step is within the 90-degree sectors, we can further divide into small subdivisions. As mentioned before, it can be divided equally. And if we have a higher resolution to have a small degree intervals, the calculation may be easier. So because of this, for this particular working example, we use 10-degree interval. So equally divided into 9 divisions. So next one is in the radial direction. So we mark several marks. So that is about with the radial distance increment as 0.5 h. So later we will show that this is for easier reference. And then we introduce some general principle how we can use the simplified approach to make our calculation easier. So the first one we need to bear in mind is within the 2 times of the target building height. So this is the distance. If the objecting building, they are within the height, which is 2 times of the target building. So then if we look at this counter plot, that means this one. So this is the horizontal distance. If this is within 2 times, of our target building. As long as the objecting building, they are taller than 90% of our target building. So you can see the sheltering benefit is bigger than 0.7. So the horizontal is the distance, how far the objecting building to our target building. The vertical is how tall the objecting building relatively to our target building. And those counterplot is the sheltering benefit. So the bigger the number, the better. And the maximum we can take is about 0.75. So if we look at about this 0.7, it has been nearly the full sheltering. So we say within the distance of 2 times of the target building height, as long as objecting building heights are taller than 90% of our target building, so they can provide nearly the full sheltering. So if we look at in details of those objecting building, so they are all bigger than 80 meters. Our target building is 90, so 90% of 90 is about 81. So then we can say all those high buildings shaded in red, they can provide the full sheltering. So this is quite easy. So just by a glance, we can identify. And then later, we say if we consider a distance further beyond 2 times to 2.5 times, we can see here. So any building which are taller than 100%, any objecting building which are taller than 100% of our target building, again, they can give full sheltering. And even though some buildings which are not 100% taller, it's not of the same height, but of the 90% of the target building height, still we can get about 0.6 on the sheltering effect. So those are the buildings highlighted in green. So for those green shaded building, we can also get a relatively big sheltering effect, that is 0.6. So then we need to go to the detailed calculation. So according to the rule, we need to identify the first and the second benefit. So actually within the 2 times of the building, all those buildings, they can provide the full sheltering. So what we need to do is we just need to pick up the first layer as the most sheltering building. So that is from tower 1 to tower 5. Then we remove them, we ignore their contribution. So further to that, we pick up tower 6 to tower 8 to provide the sheltering for division 1 to 3. They provide the full sheltering, that is a 0.7. And then for the division number 6, we pick up tower 9 and tower 10. They also give the full sheltering. Further to that, for division 4, 5, and 7, we pick up tower 11 to 14. So that gave sheltering about 0.6. And then for the remaining one, division number 8 and 9, conservatively, we ignore their benefit. So that's 0. Then finally, we have known the sheltering benefit for all the divisions. So we just simply multiply the full sheltering 1, 2, 3, and number 6. So multiply by 4. And 0.6 sheltering, that is for 4, 5, 7. So multiply by 3. And this is 0. Then divided by 9. We can calculate very quickly, just maybe in 10 or 15 minutes. So we calculate the sheltering effect for this sector. And then we repeat the same procedure. We can calculate the sheltering effect for all the 4 divisions. So then the sheltering effect calculation is completed. So after the calculation of the sheltering effect, we can calculate and also together with the directionality, so we can calculate the reference wind pressure. So here, we also want to highlight is that we have calculated displacement height. The ratio is 0.51, and the total building height is 90. So the HD is a 45.9. So then, for the EZ, which are bigger than 61 meters, so those values, actually we can use equivalent effective height, ZE equal to EZ minus HD directly. So those will be those values. However, we also need to bear in mind, if below this value, if we further still use EZ over HD, so that will give a smaller or even negative numbers. So then within the code, in appendix A2, there are equations A2 for A and A2 for B. A2 for B, it says if the Z is smaller than 1.33 times the displacement height, we need to use 0.25 Z. So that is highlighted in the blue box. And then because it is located in a flat terrain, the topographic factor is 1. So totally with the QZ flat, directionality, and topographic factor, so all multiplied together, we can calculate the reference wind pressure. Next, within the calculation of a long wind force, we calculate the reference wind pressure. So we need to go to the force coefficient calculation. For the force coefficient calculation, I think I want to highlight another thing. So we have seen the benefit of sheltering effect that can reduce the reference wind pressure. Another benefit of the sheltering effect is actually, if we look more carefully for the force coefficient formula, so actually the H over D, so it is effective building height. So that means if we have a sheltering effect, the effective building height is also reduced. So if we look at the curve, it is very clear. The bigger the slenderness ratio, so that is H over D, the bigger the force coefficient. So if we have a sheltering effect, actually, we can also get the benefits of a smaller force coefficient. For our building, so the B is 25 and D is 25. So D is because we have L shape, according to our code, figure 4.4E. So for L-shape building, the effect building depth is the average between D1 and D2. So this is calculated as 25. So then HE over D is about 1.76. Our building is 90. So if we use the original 90, so it will be 3 to 4, but now it's only 1.76. And B over D is equal to 1. So if you look at the figure, so between 1 and 2, so the calculated force coefficient is 1.17. So that's a calculated force coefficient. And then the next step is size and dynamic factor. So for calculating the size and dynamic factor, so we need to follow the following step. So the first of all, we need to calculate the size factor. So that is in equation C1.18. So within this, we need to identify the half parameter length. That's the building breadth. So then we calculated the size factor is 0.97. Based on the size factor, bring in the size factor into equation 5.1 together with the geometry information, the height, the breadth, the natural frequency, and the damping ratio. We can calculate the size and dynamic factor at the top of the building. That is a 1.04. So then further, following the equation 5.2, we can calculate the size and dynamic factor along the whole elevation. So that is given in this column of the spreadsheet. So with all those information ready, we have the reference wind pressure, we have force coefficient, size, and dynamic factor. Then by using the spreadsheet, we can calculate distributed wind load along the building. And we can also calculate the shear force and the overturning moment. So the overturning moment we need to bear in mind because later we need to see whether we need to do any scale up by comparing with a crosswind based moment. So this is the calculation of the along wind force. Torsional force. So as introduced before, within this code, we give a new formula for calculating the torsional force. And this is a very simple formula. So the torsional load is provided as equivalent torsion. So the equivalent torsion is generated by shifted lateral force from the geometric center with the eccentricity E. So then how big the eccentricity is determined, it depends on the geometric ratio, B over D ratio. So if the B over D ratio is equal to 1, so then it's a square, close to a square shape, we have the smallest eccentricity. So that is 5% of the building breadth. If the B over D ratio is quite big, for example, very wide, so the eccentricity is bigger, it's 20%. So anything in between, we do a so the BOD ratio is 6, so then it is 20%. Anything in between, we do an interpolation. In this particular working example, for WX1 direction, the B over D is smaller than 1, so it's a 5%. So E1 is about 5%, it's around 1 meter. So in direction 2, it is 8%, so the eccentricity. So then I calculated is about 3.2 meters. So then by the lateral force, by the eccentricity, for all the 4 directions, we can calculate the 4 different torsions. So for the all 4 different orthogonal directions. So finally, the torsional force will be picked as the biggest among the 4. So that is the calculation of the torsional force. Next one is a crosswind consideration. For the crosswind, this is why this working example is introduced. So we need to make a judgment whether the crosswind is significant. Within the code, actually, if you look at the flow chart, there is a diamond. So there are 3 criteria. If the building is shorter than 100, if the biggest slackness ratio in the 2 orthogonal directions are smaller than 5, if the natural frequency in both directions they are bigger than 0.5 Hertz, so then we believe they are not a crosswind resonance significant. So then we can ignore the calculation of the crosswind load. So in our case, all 3 criteria are satisfied. So then we don't need to do the crosswind checking. Then we go to the last step of loading calculation, that's the load combination. For the load combination, because the crosswind significant checking shows the crosswind will not be significant. So what we need to do is we use the lateral force from both orthogonal directions, that's from the along wind force, together with the torsional force to do a load combination. So the load combination factor is provided in table 2.1 in the COP. So we just follow the load combination factor, that's all. And regarding the serviceability, there is equation 2.4. So that provides a codified acceleration formula. That's related to the peak factor, the natural frequency, the damping ratio, the geometry information, and the mass. For the mass, we assume it is a 300 kg per meter square. So for the 1 year's return acceleration following this formula, we calculate it is about 0.024 meter per second square. So that is about 2.4 milli-G. So in the code, we also provide acceptable criteria. That is in figure 2.6. This acceptable criteria is a frequency dependence. We bring in our frequency, so it's about 0.5 Hertz. So we can see, so the acceptable criteria, even for the most stringent one, is about 5. So here we are only about 2-point-something milli-G. So we can pass the acceleration check. So there's no problem regarding the human comfort. So that's all for the structure wind load calculation. The next is for the cladding. So cladding one is relatively straightforward. So first of all, what we need to do is we need to follow equation 2.3a. That's reference wind pressure, pressure coefficient, and size factor. The reference wind pressure, still we need to follow directionality, sheltering effects. That has all been calculated, so we don't repeat again. But one thing we need to bear in mind, as Alexis has introduced in the part 1, so new feature for the new code is the reference height for all through the elevation. It is top of the building. So then we have only one reference wind pressure, that is 2.13 kilopascal. Then we need to refer to figure 4.6a. That's give the zone key definition. So where is the edge? Where is the general? Where is the corner? So then, by looking at table B1.1, we know the net pressure coefficient for different zone keys, and also following appendix C1 for the size factor formula. So for section, for edge zone, we can calculate size factor as a 1.22. So here I also need to remind, size factor is a tubular area dependent. So then we assume the glass panel is 1 meter by 1 meter. So then we calculate for edge zone, the size factor is a 1.22. For our other zone or general zone, it is a 1.96. And finally, bring in the reference wind pressure, the net pressure coefficient, and the size factor. We can calculate the positive and suctions at different zones of the building surface. And one thing I want to remind is, so here within the code, it also has a clause in the notice. It says if sheltering effect is considered, cladding pressure within 50% of half of the displacement height, we can have a further 20% wind pressure reduction. So that's why within 0.5% of displacement height, that is about 15.75 meters. So we can have a further 20% design pressure reduction. So that is all for the first working example. So then we go to the second working example. For the second working example, we introduce a further taller building. This is a tower with a 195 meters tall. The plan shape is a rectangular shape. So the dimension is B is 62.5, and the depth is about 39. And the natural frequency is actually calculated. It's about 0.25 hertz in the longer direction and 0.2 hertz in the natural direction. The objective of the case study is, so we also want to cover several unique features through this working example. The first one is, you can see, actually we have recessed corners. So we want to use this example to demonstrate when we consider the recessed corner, so with a corner modification, how the force coefficient can be calculated. The second one is because the tower is very tall, so definitely it is expected to be a crosswind significant. So then how to calculate the crosswind load. And further, if a crosswind base moment is bigger than a long wind, how a scaling up should be conducted. And the last one is, although we pass the initial check that our building can be used for codified approach, does that deem to be codified applicable? Is there any chance that in a later stage or suddenly realize, oh, maybe we still need to do a wind tunnel test? So we want to use this example to demonstrate we also need to conduct a further check regarding the need for wind tunnel testing. So again, the first step is initial judgment for standard approach applicability. So the same procedure, we don't get into details. So everything is fine. So the conclusion is the initial check shows we can use the standard approach to do the calculation. Then determination of the design wind pressure and the procedure are also the same. So first of all, we align our building, and then we identify the directionality for 8 key directions, then radar plot. Then for each 90 degree, we pick up the biggest from the radar plot. Then the next one is so calculation of a reference wind pressure. So we have some assumptions here. So first of all, we assume the building is in a very open exposure. So then there's no sheltering effect. So you can see, so in the last example, the ZE is significantly smaller than Z, but here we consider no sheltering effect. So the ZE is equal to Z. And second, we consider it is on a flat terrain. So topography factor is equal to 1. So then very straightforward by using the QZ flat, directionality, and the topographic factor. So we can calculate the reference wind pressure. Next one is a calculation of along wind force. So here, similar to before, we need to identify the H over D and B over D ratio. For this project, H over D is 5, B over D is a 1.61. So if we look at H over D is 5, so that will be the orange curve. And B over D is a 1.6, so we can identify the force coefficient is 1.37. And as said, we want to use this case to demonstrate the corner modification. So we want to remind the user, for this case, actually, we have a recessed corner. The recessed corner dimension is about 3 meters. So then we need to refer to equation 4.2 within our code, the COP. The COP here, the W is the recessed corner dimension. So by bringing in the 3 meters, bring in the 3 meters in and bring in the total building breadth, so we can calculate the factor is 0.97. So we can have a 3% reduction on the force coefficient. Then the final force coefficient is the product between the two. So that is a 1.33. So that's the final force coefficient we are going to use. After the force coefficient calculation, we need to calculate the size and dynamic factor. The first step is we need to list out all the needed parameters, the geometry information, natural frequency, and the damping ratio. So very important, as introduced in the first part, the damping ratio in 2004 wind code is constant. So normally it's recommended as 2% for RC and 1.5% for the steel. So for our case, actually in the 2019, it depends on the slenderness ratio. So later we can see that for 2 different directions, table C2/1 to calculate the damping ratio. So then the other formula will be the same as introduced in the first working example. We calculate the size factor by using building breadth. And then we calculate the size and dynamic factor at the top of the building. And then by using this formula, we calculate the distributed size and dynamic factor along the building elevation. So we can see the trend is on the top of the building, the size and dynamic factor is the biggest. And at the bottom, it gradually reduced. At the bottom is the smallest. And then we calculate the distributed wind force at different levels, and we can calculate the along wind overturning moment at the bottom. So for this direction, minus WX2, so that will be 3,569 meganewton. The next is the torsional force calculation. The torsional force calculation will be the same as what you introduced in the previous working example. So we know the B over D ratio. We identify the eccentricity in the 2 directions. And then we calculate the torsional force in the 2 orthogonal directions. And the final torsional load will be picked up as the biggest one between the 2. So next is a crosswind calculation. So this is the key point. So the reason why we want to introduce this working example. Still, within this diamond box, we need to make a judgment whether the crosswind is significant or not. So list all the criteria. So the first one is whether the building is taller than 100. So our building is 195. So very obviously, we cannot fulfill this requirement. So that means the crosswind response can be significant in this case, so that we cannot get rid of a crosswind base moment calculation. Then what we need to do next is we use the code provided a crosswind base moment formula. So that is within equation 2.2. Within this, because the crosswind is a purely dynamic effect, so it relate to several parameters, including the building geometry, including the reference wind pressure on the top of the building, and then here it is turbulence intensity and peak factor. So after this, it is actually the mean velocity at the top of the building. As I said, it is a dynamic, it's a purely resonant effect, so it's highly sensitive to the natural frequency and the damping ratio. So bring in all those factors in parameters into equation 2.2. So the natural frequency, using the natural frequency, we can calculate the peak factor. So that is a 3.5. So one thing we want to highlight is here the natural frequency is the vibration direction or the loading direction. So it's not an approaching wind direction, it's actual loading direction. So that's why we call it NY. So that means if we talk about the load as a crosswind, so the natural frequency should also be in the crosswind direction. So that's NY to calculate the peak factor. So then the gamma W, that's the load factor, partial load factor too. So in Hong Kong for wind, we normally use 1.4, and natural frequency and turbulence intensity. Then the damping ratio. So with all those parameters bring in, we can calculate the crosswind base moment in the WX2 plus direction will be 1,759 meganewton meter. So then if we repeat the same procedure for all the directions, all the 4 orthogonal directions, so we can see for all the 4 orthogonal directions, we can have a 4 along wind base moment. We can also have a 4 crosswind base moment. And for the along wind base moment is a single direction, because you can see in this figure, the black arrow means the approaching wind direction. So the orange arrow means the along wind loading direction. So you can see for the long wind, it's only one direction. It's in the same direction as the approaching wind. But for a crosswind, the blue arrow is a plus and minus, because it's purely resonant effect. It can be both plus and minus. So what we need to do is we need to check whether a crosswind is bigger or smaller than a long wind effect. So then we can make a further judgment whether we need to do any further action. So one thing we must bear in mind is, although in part 1, Alexis has introduced to say, we need to compare the ratio between the long wind moment and the crosswind base moment. But we need to bear in mind this ratio is the load in the same loading direction, not the wind approaching direction. For example, here, what we need to compare is, for example, for the vertical direction as the arrow shows. So then what we need to pick up is the 2 blue arrows, the crosswind. So that is 2432 and 2581. So in the vertical direction. And we need to compare against the long wind in the same loading direction. So that will be 3.3569 and 3.69. So then we pick up the bigger one between the crosswind. We pick up the bigger one between the long wind. The ratio is 0.7. So for the vertical direction, the crosswind is smaller than the long wind. It's smaller than 1.5, smaller than 1.5. And for the horizontal direction, following the same strategy, so we pick up the crosswind, so 1759, and a long wind in the same direction, so that's 1757 and 1821. So the ratio between the two is a 0.97, also smaller than 1.5. So it means we don't need to do the wind tunnel test, because if any of the two values that is bigger than 1.5, we need to do the wind tunnel test. But now we are satisfactory. But still, we need to check whether for all the 4 directions, the along wind are all bigger than the crosswind. So it seems for the horizontal direction, there may be a chance that because it's 0.97 is quite close to 1, there may be a chance that the a crosswind is bigger. So we double check. So we pick up the smaller along wind. So that is 1.757. So still it's very close to 1. So still, although it is the crosswind is slightly bigger, but very close to 1. So we think that's okay. We don't need to do the further adjustment. So for this scenario, we say we don't need to do any further action because the along wind base moment is equal to or bigger than the crosswind base moment. So we can use the along wind in the two orthogonal direction to do the load count directly. So that's the first scenario. And the second scenario, we change the parameter a little bit. So what we do the revision is originally for x1 direction, we assume the natural frequency is a 0.25 Hertz. So this time we reduce the natural frequency in the x1 direction to 0.21. So then we recalculate all the along wind and the crosswind. So especially the crosswind, it is very sensitive in this direction to the natural frequency. So as what is highlighted in red, so in this direction, because we reduce the natural frequency, so it is increased from the previous 1.759 into the 2.175. So that is increased. So let's do the comparison again. So for the vertical direction, there is no change because we don't make any further adjustment. For the horizontal direction, because we have increased the crosswind base moment. So then this time, in this direction, the crosswind is bigger than the along wind. So the ratio is 1.16. But still, it is smaller than 1.5. So that means it's okay. We don't need to do the wind tunnel test. However, if we see in this direction, the horizontal direction, the crosswind has already been bigger than the along wind. The ratio between the two is 1.16 and 1.21. So we need to use these two as a scaling factor to multiply or scale up the distributed along wind force in those two directions to make sure the finally adopted design wind load can cover the crosswind base moment effect. So this is the long wind force need to be scaled up. So this is the second scenario. And third scenario is we further reduce the natural frequency in the x1 direction. We reduce it into 0.15. So in this case, the crosswind base moment is increased substantially. So that is increased to 3272. So again, let's check for the horizontal direction. So now this time, if we pick up the biggest value between the crosswind and along wind, the ratio becomes 1.6. So exceeding 1.5. So then according to the code, if the crosswind base moment is larger than 50% than the along wind base moment, then the codified approach doesn't apply anymore, and a wind tunnel test approach will become compulsory. So then need to do the wind tunnel test. So that means, so through this working example, actually in the exercise, so even we pass the initial checking, it doesn't imply it's 100%. There's no chance to do the wind tunnel test. So still, in a later stage, after we have calculated both the long wind base moment and the crosswind base moment, we need to do a further checking. Yeah, this is also a very key character want to be demonstrated through this working example. And then finally, we go to the load combination. So what we need to use is the along wind force and also the scaled up to the along wind force. So to make sure that the adopted design wind force will not be smaller than the crosswind base moment. So the scale up to along wind force and the torsional moment to do the load combination, following the load combination table in the code. And finally, it's the human comfort check. For the human comfort check, similar as before, we bring in all the parameters. And for the 1 year acceleration, we are about 0.25 Hertz. So the threshold of the criteria is about 6 or 7 milli-G. But our calculated acceleration is only about 3 to 3.5 milli-G. So again, we pass the human comfort checking. So there's no problem for the human comfort for this actual example. And then it's the cladding pressure. So for the cladding pressure, this time we assume a panel size of 2.5 meters by 2.5 meter. So the half parameter length is 5 meter. And the procedure will be exactly the same as what we introduced before. So we follow the figure 4.5a to identify the zone key. So then for different zones, based on the the panel size, we can calculate the size factor. And also for different zones, by referring to table B1.1, we can get the net pressure coefficient. And finally, the reference wind pressure is the top of the building, that's QH. And then, but multiply all those together, we can calculate the positive wind pressure and the negative wind pressure. So that will be the calculation of the cladding wind pressure. And this time, because there is no displacement height and no sheltering effect, so everywhere the cladding pressure are the same, all through the elevation, but the corner and the general zones, they are different. So that's all for the working example presentation today. And later we will have 15 minutes break. And so don't walk away. Welcome you to be back. And we have a Q&A section after the 15 minutes break. And welcome, you can share with us with all your questions or queries. Yep, thank you. See you later.
Alexis 同埋立川嘅介紹，咁而家咧就到 Q&A 嘅環節啦。咁就睇翻咧大家 post 咗嘅 question 咧，第一條咧我哋就最多人想我哋答嘅咧就係 how to cater the torsional moment in building if diaphragm cannot be tight because of large void。咁呢條咧我就想請 Alexis 幫我哋答嘅，咁就麻煩 Alexis。
好，或者我先翻轉頭去解釋翻少少關於個 torsional moment 嗰個 introduction 個原因先。其實喺新嘅規範我哋做咗啲 literature research 啦，同埋基於呢個wind tunnel test 嘅 result 咧，大家係知道到就係話，當一個風吹埋一個 building 嘅時候咧，佢唔係完全係 even 嘅，佢係有一個可能有一個好 short term 嘅 distribution 嘅 response 喺度嘅。咁所以咧，其實咧，我哋依家講緊個 torsional moment 咧，係因為呢個 uneven 嘅 distribution of 嗰個 pressure on 個 building 而導致到有呢個 torsional moment。所以呢個 moment 嘅 application 咧 ，in one way 就係 apply to 個 geometrical center， 就同呢個 dynamic 嘅 behaviour 有少少唔完全 related 嘅。但係亦都係 the same time 就知道喺 wind tunnel test 入邊咧，又反映咗另一樣嘢出嚟，就話一個 building 有 dynamic response 時候，佢亦都會有一個 torsional moment 嘅 component 出現，咁所以 for application 嚟講喺個曲咧，我哋依家係 define 咗佢係 apply 喺個 geometrical center 喺個平面上面 offset from 個 center，right？ 咁但係呢條 question 亦都問咗個問題，就話如果個 diaphragm 有一個好大嘅窿唔 tie together 嘅，咁因為我 imagine 呢個 situation 咧唔係好清晰啊少少。如果如果有 building 中間等於劏開咗，咁係咪即係等於其實係兩個 building 嚟嘅咧？如果係兩個 building 嘅時候，你又要當係兩個 building 咁去 treat 佢。 如果你只係中間有個大窿，亦都係 tie 住咗嘅話，咁你就可以用一個 flexible diaphragm 或 situation 去 tie up 咗個 structure， 而去 behave 翻 as one building。咁所以要有少少 engineering judgment 喺入邊咯。我希望咁解釋得到呢個問題。
好，咁就唔該晒 Alexis。咁第二條題目咧就係if the building is considered the combined effect from a long wind, a crosswind, and torsional wind, does it mean that we don't need to consider wind U and wind V? Also, for the combined effect of a long wind and crosswind effect, do we need to consider in both element design and stability check? So I would like to invite Leptun to answer this question. Thank you, Leptun.
Okay. I think generally the understanding is correct. And so the load combination, consider the two orthogonal directions and the torsional direction. Actually, it can generate an equivalent effect or even cover more comprehensive loading actions compared with the X and Y and U and V. So putting it in another word, the current load combination provision in 2019 regarding the combined loading effect is more comprehensive than what is provided in the 2004 Wind Code. So because of that, the 24 load cases from the load combination table in the 2019 are sufficient. So we don't need to separately calculate the U and V direction. So that is to answer the first question. And to answer the second question, so does this need to be considered for both stability checking and element design? So I think yes, it needs to be considered in the stability checking. And for element design, if this talk about the member design or capacity design of structure members, yes, because it is a part of the strength calculation or strength checking. But if the so-called element design is talk about cladding pressure, so that will be another concept story. Because when we talk about the long wind or crosswind, it talk about the overall structural loading effect. So we talk about the overall structure design or the structure member design. But for cladding design, so that is not talk about the global effect. It's talk about the local cladding pressure on the building surface. So that needs to follow the cladding calculation procedure in flowchart 2.2. So for example, we need to use the reference wind pressure. We need to use the local pressure coefficient together with the size factor. So that is how the cladding pressure is calculated. Then how to calculate the strength of the supporting members of the cladding. So then we apply the cladding panel wind force. So then all the wind force will be summarized together on the supporting members. Then the supporting member is calculated. So there are two different calculation systems. If the element design refer to the cladding design. So it depends on how do you interpret your so-called element design. Yeah, that's my answer.
好 ，thank you 林總。咁第三條問題咧就係關於H over 500嘅。咁according to Wind Code 2019, do we still need to use H over 500 for the top drift limit or using acceleration limit？ 咁呢度咧就都想解釋翻，其實 H over 500係一個 deemed to satisfy 嘅數字，就係 concrete code 同埋 steel code 啦。咁而家我哋 Wind Code 出咗呢一個 acceleration criteria 咧，其實係一個 option 嚟嘅，即係 RIC 咧可以選擇用翻 H over 500呢個 deemed to satisfy 嘅 criteria， 亦都可以選擇咧去 assess 個 acceleration 去證明個 serviceability limit state 嘅。咁所以咧兩個暫時都係並行，係 RIC 可以採用。咁至於日後咧，我哋其實喺 concrete TC 或者 steel code TC 咧，其實都會將呢一個議題咧擺上去傾。咁日後究竟係點樣去留低啊，還是係有改變咧？咁呢個我哋將來會再同業界去溝通，即係我哋決定咗之後會再通知翻業界嘅。咁暫時都係兩個並行 ，RIC 係可以兩個都選擇。咁好，咁第四條問題咧就係、關於 temporary structure 嘅 ，Do we have to apply those force coefficient to temporary structure while using 37% of the wind load? So, Latun, can you help us to explain a bit more about this one?
Okay. I think this is written clearly in the COP. For the holding design or cover walkway, if it allows to use a reduced wind pressure, that is 37% of the codified wind pressure. So here I want to further explain what can be used, what cannot be used. What cannot be used is the directionality, sheltering effect. So directionality and sheltering effect shouldn't be used together with the 37%. But what should be used is if there's a topographic impact, the topographic effect should be considered. And also when we do the structure design or the cladding design, the size factor should be considered. Yeah, so this is my answer.
OK, thank you, Lepton。咁跟住下一條咧就係how to obtain an accurate and latest building height for all surrounding buildings。咁呢一個咧其實我哋喺曲嗰度冇列明一個指定嘅方法嘅，咁但係業界其實亦可以去地政處嗰度買佢哋嘅地圖啦，因為佢哋個地圖咧係可以睇到附近樓宇嘅高度同埋佢嘅坐標嘅，咁所以用呢個坐標咧都可以計翻個距離。咁呢個咧都係我哋認為係即係覺得係可以信賴嘅一個記錄啦。咁但係如果譬如 RIC 佢有自己嘅方法，佢譬如可能用我哋嘅批准圖則去揾翻，或者係佢自己本身有個 survey 嘅話咧，呢個都可以同我哋喺入職嘅時候溝通嘅。咁但係我哋亦都覺得地政總署嗰個其實大家都可以好方便可以使用㗎啦。咁另外仲有一條咧就係whether shelter effect can be applied by buildings in the same development。咁呢度咧就都想解釋一下咧，喺我哋曲嘅 page A2 section A2 入邊咧，其實都有解釋到嗰個sheltering effect 咧，其實係講緊 direct shelter from other buildings surrounding a site。咁所以咧呢度咧，我哋都會係理解係你個 development 周邊嘅樓嘅。咁所以咧喺同一個development 或者喺個 site 同一個 lot 入邊咧，其實我哋都唔 expect 個 sheltering effect 係考慮在內嘅。好，咁跟住就到下一條啦。When a building is more than 100 meters in height, the code requires the natural frequency to be calculated by means of analysis instead of 46 of H. In the analysis, do we need to formula a full building model just for obtaining the natural frequency, or we just simply use the natural frequency from wind frame model? 咁或者呢一條即係可能又有 structural 嘅元素，有 wind 元素，或者我請 Alexis 去幫我哋去解答咧。
係啊，區份入邊state 咗就係好似頭先嘅問題咁講啦。如果超過100米嘅時候咧，你就可以你就需要做一個呢個 dynamic analysis 去 assess 嗰個 actual building 嗰個natural frequency。咁其實你去assess 個 lateral frequency 有好多方法嘅，或者可以做一個 full building model， 將所有嘢放晒落去，咁係一個方法嚟嘅。咁或者其實有另外一種，例如喺美國曲入邊做法就係可以有啲 simplify approach， 就係話某一啲 frame 只係 running surface for 一個 direction 嘅，而有啲 frame 就 running on the other direction， 而佢唔 couple together 嘅。咁其實呢個係 based on 少少有 engineering judgment 嘅元素入邊咯，就唔係淨係 wind engineering 咯。咁你係要assess 得到究竟你個 building 係用一個乜嘢嘅體系結構體系去 resist 呢個風嘅，咁就 based on 你嗰個體系嘅 definition 去計呢個 lateral frequency 咯。咁我唔會所以有少少呢個需要係有少少嘅 engineering judgment 喺入邊咯。
好，唔該晒 Alexis。咁跟住咧，我哋就掃落去下一條啦，就係 how to determine the loaded area of size factor。係啦 ，OK，so 其實上少少都有另外一條咧，就係 is size factor required for to apply on building elements like canopy or projected structures. So maybe Lepton, can you explain a bit more on the size factor?
Fion, can you go to another question first? I have a PPT slide. I'm looking for that.
好啊，好啊。咁或者喺阿律敦準備嘅時候咧，我哋就我哋再睇下先。As stated in clause 2.5 for hoarding in covered walkway and the like, 37% of the wind pressure will be used, but not the 係呢個其實頭先都講咗啦。咁或者呢度再重申多次啦，就係directionality factor 同埋 sheltering effect 咧，其實喺用咗37% 之後咧就唔可以再用噶啦。咁但係 topography 啊、size 同埋 dynamic factor 咧都依然可以用翻嘅。咁跟住就係係啦。咁for building with irregular shape, there are many ways to draw the enclosed rectangle. How to decide which pair of dimensions to use for wind calculation? 咁呢個或者Alexis可唔可以幫我答一答？
我哋嘅睇法，因為其實今次個曲入邊嘅upgrade 或者 adjustment 咧，其實有少少 relate to 個 dynamic property of 個 building 嘅，所以我嘅建議就會係當你去 draw 呢個 enclosed rectangle 嘅時候咧，你可能係需要就翻喺嗰個principal axis 入邊你個 dynamic property 去同你個 dynamic property 相應啊。當你個 dynamic property 最弱個 direction 嘅時候，係會產生最大嘅 crosswind situation 啊嘛。咁所以當你去擺你個 enclosed rectangle 嘅時候，而係 fall within 呢個 consideration 嘅時候咧，就會俾到佢嗰個最 adverse 或者一個最 realistic 嘅 effect 俾到你睇到咯。或者立專想有少少補充係咪？
好。Okay, following what Alexis has just introduced, I think I want to draw the attention from all the users is this time when drafting the 2019 code, actually regarding the coverage of irregular building forms, we have moved one step forward compared with the 2004 wind code. So this you can see from the presentation in Alexis part 1. So there is for example, the X shape, L shape, Y shape, and also C shape. So all those irregular building forms has not been well defined. But from the code drafting process, the industry also contributes lots of valuable suggestions. So one comment is, so even though we have a more comprehensive coverage regarding the irregular building forms, but in Hong Kong, we are quite a unique metropolitan. So the building forms has a big variety. So then to avoid a big portion without the reference to the force coefficient to be wind tunnel tested, so can we provide some other supplementary guidance? So in order to achieve this, to answer this request, actually in the EN, so here what I'm showing is the explanatory notes in section 4.2.4. So I think maybe later after the briefing session, you can have a more detailed looking at this one. So in the page 18, it says, sometimes if the buildings which are not well covered within the COP, so the following rules can be used. So generally speaking, what it says is, so this represents a very irregular shape, a highly irregular shape. So we draw equivalent rectangle. So for this is we ignore this void. So you can see the blue part. So this is the field first, and then we consider this the biggest projecting breadth. So we consider this is the one direction. So that's the biggest projecting breadth, and there is any shape which is not perpendicular to the wind approaching direction, we can take into account of the corner modification. So this is the second point. You can see clause 4.2.3 may be used to assess the corner effect. And the atom B is the re-entrance surface should be ignored. So this is this part should be ignored. So further to that, so we have identified where it is the direction for the projecting breadth. So for the depth, we also need to calculate the D. So for the D, it says the D should be taken as the smaller one or the minimum between the actual depth. So that's the two furthest distance in the approaching wind direction. So that's the actual D, and the B over 1.8, whichever is smaller. So we have 2D. So the smaller one, that is should be taken. Okay. So then this is finally how the equivalent rectangle is drawn. So for example, in this direction, so the actual depth is smaller than D over B over 1.8. But for this direction, so the actual depth is bigger than B over 1.8. So the B over 1.8 is taken. So this is how irregular shape conditions the equivalent rectangle should be drawn. So otherwise, if we have more time after the briefing session, you have a more detailed looking for this this session in the explanatory note, Phil.
Yes, thank you. So how about the question on the size factor?
Size factor, give me 1 minute.
OK， 好，唔好意思啊，因為技術嘅問題啊，得仲要再準備。咁或者我哋跳到去後邊嘅先，咁就OK。In the 2019 code, is there any requirement on channel down effects which similar to clause 6.2 of 2004？ 咁呢個或者 Alexis 可唔可以解釋下？好。
Okay. I think for this one, so actually the new wing code, I think both Alexis and myself, so during the general section and the working example section, we have introduced. So for the cladding design, a significant change is now the reference height has been taken as the top of the building. So that is consistent with all the international standard. And because we have already used the top of the building, so that has been definitely covered with wash down.
Oh, it's wash down. Sorry. 已經 cover 咗啫。
即係呢個04曲嗰個 channel down effect 其實已經係我哋今次用咗 top of the building 咧，其實就係反映翻嗰個真實嗰個 behaviour。咁所以大家留意，如果你計嗰個 cladding design 嘅時候咧，就唔再係好似以前咁用翻佢個 cladding 個 level 嗰個 wind pressure， 係應該係攞個 top of 個 building 嘅。咁仲要留意咧，就係如果佢係podium structure 上邊 tower 嘅話，而個 tower 係好近嗰個 podium 嘅 edge within 一個距離，大家可以睇翻曲嘅 figure 4.6嘅。咁其實佢嗰度入邊都4.5 sorry 係啦，佢入邊都有講過咧，如果個 tower 個 building 係好近個 podium edge 嘅話咧，其實咧係要考慮係 tower 嘅頂，即係 even 係 podium 嘅 cladding 咧，你其實都可能要用 tower 嘅 top level 咧去做嗰個 cladding 嘅 pressure。咁所以咧，大家呢個係都值得留意，係喺我哋三曲嗰度。
唔該晒，俾我。
咁就are you ready on the size factor? Or I just jump to the question behind？ 係啦，咁或者好，咁跟住咧就有下一條就係torsional load dealing with eccentricity。呢個其實頭先between load centre and 個 building's rigidity centre。咁呢個講咗，其實我哋今次個 torsional wind 咧 ，torsional load 咧就唔係考慮嗰個 structural 個 shear centre 同埋個 wind load 嗰個 difference 嘅。咁呢個因為不嬲其實都喺嗰個 ETABS model 或者係個 computer model 已經充分考慮咗。咁呢個係特別因應其實個風唔係 uniform on 個 building 係 uneven 咧，其實個風本身都會製造一個 torsion。咁呢個係一個額外嘅 loading 嚟嘅，咁所以即係有分別。OK， 好，咁Lecton 會行翻轉頭啦，咁就講翻個 size factor 嘅。OK，thank you Lecton。
think I use a specific example to answer the question. So the question is, so how the size factor should be considered. So when doing the cladding design. So I think this here we're talking about a very real example. So for example, if you can look at my PPT slides, we talk about actual glass wall. So what is highlighted here, we call, so the pink one, we can see it's a glass panel. It's a glass panel. And then this one, it is a glass panel supported by the mullions, okay? So then if we look at this glass panel, so we say for the glass design, the loading area is the pink one, okay? So then for the half parameter length, it will be A plus B. So that's the half parameter length. So how to do this glass panel design? We should consider the size factor. And then if we talk about the anchor, here, so then we know that those points, they will share the wind loading from the fall panel. So actually for this anchor or this fixing, it will be this tubular area. So then the half parameter length will be this tubular area, okay? So this is another case. And the third one is, if we're not talking about this, we talk about a transom. If you can look at so for a transom, it will be something like this. So this will be the tubular area for the transom design. So then the half parameter length will be this one. So for the mullion will be the same. So it will be trapezoidal like this. Okay, so it will be trapezoidal like this. So then the half parameter length will be half of the trapezoidal parameter. So this is to answer the question. So by using the new Win code, so how the size factor can be calculated subject to the different loading area field.
Yeah. Okay, thank you, Lepton。咁係啦，跟住咧就去到後邊咧就有一條就係關於directionality factor 嘅。咁佢嘅問題就係 according to the EN A1.1, it mentioned that some sites are sheltered from the stronger typhoon winds by topography or other buildings. The variation below 0.85 is potentially useful in this case. Does it mean that we cannot apply 0.85 directionality factor for remote site without building or topography shelter? 咁呢個或者Lam-Shan, can you supplement on this?
Okay. I think this may be a misunderstanding about this statement. I think this statement is to give a little bit more details. So how some directionality factor, so you know that in our code, the directionality factor is between 0.8 to 0.85. So this clause is to say, so how the further reduction from 0.85 to 0.8 is achieved. So it talks about, if you think about some directions, for example, from north or northwest, actually it's the entire mainland China continent. So if wind blows from that direction, it need to come across a very vast land terrain. So that topographic impact is or the ground roughness is much more significant compared with our Hong Kong wind code open water exposure. So that's why we say that in those directions, we can have a further reduction from 0.85. So that will be go to as low as 0.8. So here, I think the person who reads this query misunderstand this. So we should say the directionality factor can always be applied no matter where your site is located, because in the EN explanatory note, this topographic impact, we call it regional. It's a much bigger area. It's a much bigger area. So normally our talk about topographic impact, for example, the topographic testing, will only talk about 5 kilometer or 10 kilometer is a small range. But in the EN, what is referred to is a much bigger extent or range. So to simply answer the question is, yes, it can be applied no matter what the topographic condition is. But bear in mind is the topographic impact will always need to be investigated separately. Yeah.
好咁呢度我都想補充嘅，其實咧我哋呢一個directionality 咧，其實最高就係0.85啦。咁即係咧，其實最基本咧，大家都有15% 咧係有個 discount 喺度嘅，同04曲嗰個比較。咁所以呢度咧，大家即係可以應該係開心嘅，即係我哋其實比04曲咧，我哋最少咧都有10% 少咗嘅 wind load 嘅。咁不過都要留意咧，其實喺曲入邊有一句咧就話 directionality factor does not apply to secondary building 嘅。咁即係話頭先阿 Legend 都講，佢呢一個 clause 就係唔論你個 building 擺邊，但係如果你個 building form 係一個 circular building 嘅話咧，其實呢個 directionality factor 就唔可以用㗎啦。咁所以大家要留意翻嘅。咁喺曲嗰度都有相關嘅 clause， 大家可以 check 翻。Any supplement on this？ 好 ，OK。咁好啦，咁然之後咧就到下一條啦。When calculate torsion load, should the along wind consider the scale of factor due to a crosswind？ 嗱，我嘅理解咧就係用 along wind 嘅 ，am I right？ 係啦，咁就係啦，所以咧大家就留意啦。其實嗰個 torsion load 咧係用本身 wind pressure。So how about directionality factor？ So sheltering effect, maybe can you explain more on this?
Okay, so in the working procedure, so first of all we calculate the along wind force. So for the along wind force, it include everything it should consider. So for example, the sheltering effect, directionality factor. Okay, so after the along wind force is calculated, then we following the provision in the code. So based on the B over D ratio, so we give it eccentricity. So then for 2 orthogonal directions or for the 4 orthogonal directions, we can calculate 4 different torsional load. So then we pick up the biggest one. So this is purely based on the along wind load before any scaling up. So for example, if even later it shows the crosswind space moment is bigger than the along wind, and the along wind need to be scaled up, but the torsional load is still based on the original unscaled along wind force to calculate the torsion.
Okay, thank you. So 咁下一條就係 how to consider uplift wind force in the load combination if it is a portal frame structure with sloped roof. So maybe Neptune, can you help me?
I think so. This is normally talk about some low-rise building. So for the low-rise building, actually in this COP we mentioned, we can refer to national standard. So Phil, maybe you go with another question and I'll come back to you.
咁就等我睇睇先啊。咁或者我答啲後邊先啦。有一條就係 for wind tunnel test without considering building removal scenario, should we only consider 80% of along wind loads from coal as well, and we need to consider crosswind as well？ 咁呢個咧，我相信就係指咧我哋曲 figure 6.1啦，咁佢入邊都有講，或者 clause 6.4啦，就係講個 minimum load from， 即係喺 wind tunnel test 吹完出嚟，究竟嗰個 minimum load 係點樣攞嘅？咁如果佢嗰個情況就係冇掹樓，咁佢係應該係0.8曲，就唔係又唔係佢我哋個 terms 就唔係曲 along 啦。咁所以呢個曲呢個字咧係包含咗咧係需要考慮埋 crosswind 呢一個元素喺計嗰個 capping limit 嗰度嘅。 咁相反咧，如果係有掹到樓，即係話佢吹兩個 scenario，一個就係佢 existing 嘅情況，一個就係咧跟我哋 sheltering effect 嗰個 clause 選擇去掹 most beneficial building 嗰個 case 咧，咁其實係可以用0.7 曲 along 嘅。咁呢個 capping limit 咧，其實只係需要考慮 along wind 呢一個wind moment 係同埋咧，其實大家都留意呢個6.4 clause compare 嗰個 capping limit 咧，係 apply 喺個 overall base moment 嘅，就唔係喺每一層個 story low 去逐層 cap， 而係就係 wind tunnel 吹完出嚟，佢有個 total base moment 啦，咁然之後去 compare 曲計出嚟嘅 total base moment， 去攞個70% 或者80% 去做個 capping 嘅。咁希望大家即係日後如果睇 wind tunnel 嘅時候會留意翻呢樣嘢，因為我哋亦都唔希望咧wind tunnel 吹出嚟嗰個 building pressure distribution 咧係受到我哋曲嗰個 wind profile 所影響啦。咁因為 wind tunnel 吹出嚟嗰個 profile 咧係即係我哋相信係會比較準確啲。咁所以我哋其實個 capping limit 咧就只係我哋 cap 個 total base moment 嘅，即係個 base 嘅啫。咁就Are you ready? OK. 咁就翻上去咧，就係sorry，我都喺呢度uplift wind force in low combination if it is a portal frame structure with slope roof.
I think the question is to ask how to calculate the question is to ask how to calculate the section or negative pressure on the roof. So I think this not only for the portal frame, but also for all the low-rise building for the roof calculation. I think we can refer to figure 4.6b. So you can see that is to the zone definition on the roof. The zone definition on the roof. But for this one, we just don't have the upper tower, so it will be something like this. So the zone definition of the roof. So after we identify the zone key, we can. So this is the zone dimension. So the extent, where the different extent, and then we need to go back to the table. So the table, yes. So I think for the portal frames, so it also applies to whether it is smaller than 30 degree or whether it is bigger than 60 degree, and whether any interpolation between the two is needed. So I think if it is, for example, if it is less than 30 degree, so then what we need to do is just following the zone key, identify the suction zones. But what I want to remind is if it is for cladding design, if it's called for cladding design, then it will be something here everywhere. So it's most onerous. But if it's for structure design, maybe we don't need to be that onerous, because if wind blow from this direction only here, this is the corner. For the remaining one, for example, for this one, it will not be that onerous. So that's why at the very beginning, I recommend we look at this first. So you can see for a particular wind direction, it gives, say, this is the highest section, and this is the second most onerous section, and this is the less onerous location. So for structure design, it's better to refer this one. That will give us not the most conservative result, I feel. Yeah.
Okay, thank you. So the next question is, okay, it's about a crosswind. I think it's a crosswind calculation. How can we obtain the mass of building above 2 HB/3? So, do you have any idea about this one?
So so this talk about so when we do the acceleration calculation, so we need to provide the mass of the top 1/3 of the building, because aerodynamically the top 1/3 is the most important part. So how to do that? I think if we have a finite element model, so for example, both ETAPS or sub 2000, so that will be a mass source definition. So within our code, we also says, so in wind design, so here we require the mass source definition should be from the loading, it will be 100% from the dead load and 25% from the live load. Okay, that's the mass source definition. So then if we have already got the finite element model, so then we can get all the mass for each story, right? For each level or for each story. So what we need to do is we just accumulate the total mass on the top 1/3 of the building and divide it by the volume. So H divided by H, B, and D. So then we can calculate the mass density on the top 1/3 of the building. Phil.
OK，thank you。咁因為時間而家都差唔多4:53啦，咁我或者揀多2條啦。咁其中呢一條咧就係I think is referring to when Alexis mentioned about or maybe Leptune is mentioned about sheltering effect. You mentioned 500 is not a hard number. What if I take 300 for the radius? Is the HD still the same? 咁呢度或者我講少少，Leptune 你有補充可以之後講。咁其實呢度咧sheltering effect 咧其實係一個 beneficial 嘅 effect 嚟嘅。咁其實如果 RSC 簡單啲講，其實佢可以 take one， 即係話佢唔攞呢個 sheltering effect 就用一個 full wind 去做個 building design 嘅。咁至於如果真係想攞呢一個beneficial 嘅 effect 嘅話咧，其實佢可以選擇喺個 site 嘅外邊跨個圈去計翻個 sheltering 嘅 effect 個 degree， 即係話攞個 HD 個數係幾多。咁其實個圈嘅大細咧越大，你想象下，如果座樓外邊越多樓遮住佢，嗰個 sheltering effect 一定係越大啦。咁越細，咁佢只係攞咗面嗰陣，咁可能嗰個 reduction 咧就會相對細啲啦。咁至於究竟攞一個幾大幾細咧，其實呢度係同個 designer 嘅考慮有關嘅。即係話如果你彌敦道、旺角，你其實跨個500或者300咧，其實你要攞嘅 sheltering 咧，其實基本上差不多，因為你前排嘅樓咧已經擋住咗，你可能已經攞咗好多嘅 benefit。咁所以咧喺呢個情況，你可能攞300或者 even 100，可能已經有你想要嘅效果。咁你再做500米嘅 radius 嘅時候，其實可能你花嘅功夫好多，但係其實嗰個效果未必係咁大。咁所以呢度咧，其實我哋冇一個硬性嘅規定嘅。咁我哋曲嗰度係有一個距離嘅，就係6個 building height 係啦，6倍嘅 building height。咁但係咧呢度我哋唔係一個即係必然嘅數嘅，即係因為其實我都明白喺計算嘅過程，你個圈越大，你樓越多，其實花功夫亦都好多。咁我哋唔一定係要攞個6H 嘅，其實你攞大啲攞細啲，其實係真係 designer 可以自己考慮。咁如果你覺得你想攞到多啲嘅 benefit， 你就跨個大啲嘅圈去計。咁攞細啲咧，其實亦都我哋冇問題。Even 最直接就係我唔攞 sheltering effect， 咁亦都可以嘅。咁所以呢度咧，大家唔使太即係緊張呢一個數字係啦。咁或者Leptune，if you want 係 any supplement？
Yeah, I think exactly as what Phil mentioned. So if you want to reduce the radius, yes, you will have a smaller sheltering benefit. So it is a compromise. If you draw a bigger circle, then the calculation difficulty will be bigger. If you draw a small circle, yes, it's the calculation will be simple, but the shelter benefit is smaller. Just one thing want to emphasize. So never go beyond 6 times of the total building height, because the formula has been there. So anything beyond 6 times of the target building height, there will be no sheltering at all. So there will be no effort, no output. So if you want to increase the radius, but but please do not increase or go beyond 6 times of the total building height. Yeah, that's all, Phil. Yeah.
好，thank you Lutton。最後一條或者我睇一睇先啊。係啦，頭先飛過有一條係 A&A 嘅，或者我呢度我揾唔翻條題目，或者我好簡單講啦。其實就如果 A&A 係加咗一啲 frontal area 嘅話咧，其實係需要根據 APP 117入邊嘅考慮去做嗰邊 design 嘅。咁如果有需要嘅時候咧，其實係即係如果增加個面積係即係個如果 extension 好大而令到嗰個 frontal area 係增加多咧，根據APP 117咧，其實係需要用一個prevailing wind 曲去做啦。咁所以喺呢個情況，如果大過10%或者個 stiffness 係太大嘅話咧，其實就係都需要跟翻我哋2019曲去做。咁呢個大家要留意翻。係啦，咁 OK，咁時間 I think time is running short, so the last one I would like to talk about the language medium. We noted from the audience that some audience would like us to have an English version of the briefing section. So please accept my apology that the first one is in Cantonese. But if Buildings Department is going to organize the third briefing session, we would very likely that the third one would be in English. So 咁今日咧就多謝大家收睇同埋收聽我哋第2次嘅簡介會啦。咁時間亦都差唔多，咁希望今日咧可以即係盡量令到大家更加了解我哋2019年守則嘅新嘅 features 同埋點樣用啦。咁如果真係今日有問題，我哋係未能夠解答到嘅話咧，咁都歡迎各位咧係send email 去俾我哋嘅 inquiry 嘅。係啦，可唔可以吹一吹？係啦，咁如果咧真係有問題係好想我哋再解答嘅話咧，就歡迎大家去 send 去我哋呢一個 BD 嘅 inquiry 嘅 email， 咁我哋稍後咧會再覆返大家㗎啦。咁今日時間都差唔多，多謝咁多位，咁希望我哋喺第3次 briefing session 可以再見到大家，咁多謝各位，好，再見。